of matter. And so you can see here that we've got neon, and neon's in the gas state right now. And what we can do, and this is a nice pHet simulation, is we can start to decrease the temperature and check to see what happens as we decrease the temperature. And so as we start to decrease the temperature, you'll start to see that the molecules are starting to do what?
Together.
Yeah, they're starting to come closer and closer together. And so if I click on this and go right to the liquid phase, you can see that in the liquid state here, they're still moving around close together, but they're kind of bouncing a little bit. And so this one happened to just kind of take off and gained a little bit of energy and took off into the gas state, and so did that one right there. So because they have weaker forces, they're able to come apart from each other and move off into that gas state. So now if we start to cool it a little bit more, then what will eventually happen?
They don't
Right, then they're gonna turn into the solid state. And so you can see the temperature up there as being 6 Kelvin, 5 Kelvin, right down there or right up there. And so then if we just click on the solid state, then you can see that it forms a type of structure that we would call a what? A crystal. Awesome, a crystalline type of structure. Perfect. Okay. Now if we went back to the gas state and we click on something like water, and so you can see the water molecules moving around in the gas state, and it's at 809 Kelvin, and we start to cool this down. In Kelvin, there's a difference of 273 between Celsius and Kelvin. So at what temperature in Celsius will water start to condense and turn into the liquid state?
Zero.
To turn from a gas into a liquid.
Oh, 100.
Perfect, 100 degrees Celsius. Okay, which means it would be what in Kelvin? If you added 273 to 100, you would get 373. And that's where it actually would have started turning into a liquid, is at 373 Kelvin. So now what we're going to do is we're going to start to cool it even more. And so you can see that these are flowing past one another, but they're not taking up the container, the entire container in this liquid state. So now we're going to cool them down even more. And what happens with water that didn't happen with neon? They are forming what? We would say that this is a solid in what? In crystal structures, right? So they're still crystalline, very good. They are still in a crystalline structure. Let me just go to that solid state. They are in a crystalline structure, but the only difference is now they're not as densely packed, which is why water does what above its liquid? It expands and it floats, okay? Typically, substances don't float in their own liquids. Water's different when it comes to this, and we'll talk a little bit more about that as we go through the unit. So in this case here, because it expands, water forms these crystals when it's in the solid structure versus neon or argon or oxygen, where they're actually more densely packed. Water in the solid state is not as densely packed. And so this is kind of a very common question that a lot of people ask, including my own kids, will say things like, why is it that ice floats above the solid? Shouldn't it be more dense? When solids, we know, are the more compact or the more densely packed type of phase. Why isn't that? Well, it's because you get these patches in between of air. Okay. So let's go to the notes. And so what we're going to end up talking about today is, first we're going to start off just by reviewing the different states of matter. And so we'll talk about that. And then we'll talk a little bit about kinetic energy. We are also going to talk about the nature of liquids and the model for liquids and how vaporization and evaporation are different by definition. We are probably going to skip boiling point because of the boiling water with ice lab that you did. So I want you to figure that out, and then we'll come back and do the notes together. So I want you to try to look it up and research it, and then we'll come back and talk about the exact definition. By the way, on the calendar, I posted the definition for boiling so that you use that one. There are multiples that are more elementary. The actual scientific definition of boiling point is different, so I wanted you to see that and use that for your lab. Okay, and then this is delta H vape. There's a vapor pressure. We'll talk about vapor pressure. We'll talk about something called the pretty bitch, and it's not bad word, bitch. It's a female dog, so we will say it over and over again, and it's a good, positive thing, a cute little pretty female dog. Okay. So we'll talk about this this thing. We'll talk about exo and endo, which we've already mentioned before, exothermic and endothermic. And then back to the pretty bitch chart again. And I think that's where, and then, oh, nature of solids and crystal structures. So we talked about ice being in this crystal structure here that even though the solids are supposed to be more densely packed, that's the reason why it floats. And then you can see water in the liquid and then water in the vapor state. And how you can change by either adding energy or energy that's being released. And then we'll talk about the difference between melting and boiling. This is called a phase change diagram versus what we did before at the beginning of the year was called a heating curve. Remember the Britney Spears effect? Yeah. We said that the temperature remains constant as you go through a phase change. Anybody remember why your temperature remains constant? Perfect. The energy is either being used to pull the molecules apart or it's increasing your temperature. So it's not doing both at the same time. And so we come back and just review a little bit of that again. And I think that's it. And then we're back to the use of what I call my pretty big chart. So like the last 3 pages, I'll tell you all about that. All right. So water exists in the solid phase as what we call what? Ice. Good. If I want to use green, I'm going to switch this to something a little bit darker. Okay, so the liquid phase we would just call liquid water, right? And then in the gas phase, we call it?
Water vapor.
Yeah, vapor or water vapor or steam, right? A substance in one state may change to another as soon as you change what? Can you change the phases? Temperature. Good. When you change the temperature, you can then change the phase. In the solid state of matter, the particles are packed how together? Tightly or closely together. Very good. Or densely together. And the solids do not blank or take the blank of their container. They don't take the shape of their container. Very good. And they do not, starts with an F, they do not, something that, I heard it, flow. Good. They do not flow. Very good. They don't flow past one another. They are vibrating, but they're not flowing past one another. Solids are a condensed state of matter. So we say that they're incompressible. In the liquid state, the particles are relatively free to move, so they are said to flow. Good. Although they also do not take the shape, good, of their container. Nice. Increasing the pressure on a liquid has little effect on the volume, so the liquids are also described as being generally, what's the word that starts with an I? In something? Incompressible. They're generally incompressible. Nice. In the gas state of matter, all forces between the substances are now broken. We have these IMFs, but when they're in the gas state, they're too far apart from each other for those IMFs to really take effect. So the gaseous atoms and molecules are able to spread out, and they assume both the shape and volume of their container. So gases flow readily, and then a word for spread that starts with the D, bio word.
Diffuse.
Diffuse. Nice. They diffuse rapidly. Good. When pressure is added to a gas, the molecules will move. If you increase the pressure on a system, what's going to happen to the molecules? They're going to start to get what and what to each other? Closer. Good. They're going to get closer, and if they get closer, then what happens to the volume?
Increases. Decreases.
Then, yeah, they're closer to each other, so then your volume is going to become less, or it decreases. Good. Scientists came up with a model to describe why substances change from one phase to another, and they call it the kinetic molecular theory. Now, you've heard this word kinetic before, and you've heard it in kinetic energy, which is the energy of? Good, I heard it. Of movement, of motion. So kinetic energy is simply the energy an object has due to its motion or its movement. So now we're talking about the kinetic molecular theory. And this proposes that tiny particles in all states of matter, are in. So we're talking about kinetic, which is the movement of molecules. And some of you may know this. It's 2 words. It's something, something, actually 3 words. Something, something, something. So tiny particles in all states of matter are in? Motion. Motion? What type of motion? 2 words to describe it. Constant?
Rapid.
Starts with an R,
Rapid.
not rapid.
Repetitive. Repeating.
R-A, I may have heard it, I don't know.
Rap.
That all particles, if they're, imagine them moving, okay? Imagine the gaseous particles moving like we saw in that pHet simulation. Random, yay! Who said it?
Someone said it over there.
Nice, nice. Okay, very good. So these are in constant, random motion. Okay. So there are some assumptions of the theory though, because in order for them to be in constant random motion, there are some things that may not necessarily be true, but we just have to assume in order to accept this, because a lot of you are probably like, that can't work, that doesn't work. So let's talk about some of these things. The first thing is that gases are composed of particles, and usually these particles are just atoms or molecules. We take them to basically be small hard spheres with empty space in between them, okay? There are no blank or blank between these particles. If they were to keep on moving and they don't stop moving, then when they touch, when they come close together, they must not be what? Yeah, a word? Attracting. Or the opposite of attractions would be? Repulsions. Good. There are no attractions or repulsions. No, there really are. Okay, but in order to accept this theory, we basically have to say that when they come together, they're not actually sticking. They come and they bounce right off of each other and they keep on going. They're not actually attracted and they're not repelling, meaning if they're coming close to each other, they don't just all of a sudden bounce off. So if we look back at that pHet simulation that we were looking at here, when they're in the gas state, you can see that they just hit each other and then they keep moving off. So we're not seeing any attractions where they stick or any repulsions where they bounce away from each other as they're coming toward each other. But again, in reality, they really do have attractions and repulsions. Particles in a gas move quickly or rapidly in constant random motion. So I heard that before. They do move rapidly. They travel in straight paths and they fill their containers regardless of shape and volume. Good. So that means whether you're in a small container or a huge room, they're going to fill that volume. Okay, the volume of the gas is the volume of whatever the container is. Oxygen molecules move at about 622 miles per hour. So if that's true, then why can't we smell the pizza that's cooking down the street?
It dissipates too much.
Perfect, because of diffusion. Because of diffusion and absorption from what?
Other molecules.
Trees, other molecules, people's clothing, anything that's around. And due to the absorption of those. Collisions are perfectly, the word that I'm looking for here that they use is the same word that you would use to describe a rubber band. Elastic. They are perfectly elastic is what they say. And kinetic energy ends up transferring from one to another without loss. The idea would be you have molecule number 1 and molecule number 2. And they come together and they bounce. They exchange energy without losing any. And then they just take right back off, moving at the same velocity that they were moving before. So they just hit, bounce off, hit, bounce off, hit, bounce off. How is that elastic? Why do they call a rubber band elastic? You stretch it out and you let go and what happens? Comes back to how it was before. Okay? So without loss of energy. Kinetic energy remains constant and the average kinetic energy only changes when you change the what? Temperature. Nice. This is an important thing that the state really wanted you to get down. And so this happened over and over again when we were looking at state benchmarks. So we're going to just write this down one time. We're going to say that the average kinetic energy only changes with temperature. Okay, only changes when you change the temperature. All right, when a substance is heated, the particles will absorb what? Energy. Good. And some of it is stored and some of it speeds up the particles. The one that's stored we call? Yeah, I heard it. Potential energy. Nice. That's your stored energy, is your potential energy. This doesn't change the temperature of the substance because it's just being stored. It's not going to actually alter your temperature. The energy that's used to speed the molecules is called the kinetic energy. Good. And the energy, there's a wide range of these kinetic energies for the particles inside of one container. They will have different kinetic energies depending on how close to the heating source, for example, that they are. But what we do is we talk about the average kinetic energy instead overall. And so an increase in the average kinetic energy causes your temperature to also increase. So they're directly related. As a substance cools then, if you did the opposite and you cooled it down, then the particles move more slowly. Very good. And so what is true about their average kinetic energy then?
Decreases.
It decreases. Awesome. Then it decreases. Okay, so just a little bit of review of stuff that it sounds like most of you kind of already knew. Kelvin. The difference between Kelvin and degrees Celsius is how much? 273.15, but we're just going to use 273 degrees. Okay? Kelvin doesn't actually have a degree unit, it's just K. So Lord Kelvin was a Scottish physicist and mathematician, and he determined that the lowest unattainable temperature, where all movement would stop, in theory, would be negative 273. He came up with a scale where he assigned negative 273 as 0 Kelvin, calling it absolute 0. So the Kelvin temperature is always 273 degrees. If 0 is the lowest in Kelvin, but Celsius can go lower, then the Kelvin scale is always higher. Good. So it's always higher than your degrees Celsius by 273. Relating average kinetic energy to Kelvin. The Kelvin temperature and the average kinetic energy are directly proportional, just like we said before about temperature and kinetic energy. In other words, as one increases, the other also increases. So very important, at any given temperature, the particles of all substances, no matter which phase they have, will have the same average kinetic energy. So what I'm saying is, just to confirm this, is if you had something like carbon dioxide inside of a container, or helium inside of a balloon, and then you had water in a container as a liquid, and then you had a tree, okay? As long as they're all at the same temperature, then what is true of their average kinetic energy?
It's all the same.
It's the same, okay? They're all the same. Now, I want you to just keep in mind that that's different from the velocity of it, okay? And people will say things like, yeah, but what about the idea that Ke equals 1/2 mv squared is something that if you take physics, you're going to hear that over and over again. So in AP, not in this class, but more in AP, I get students that go, wait a minute, but isn't kinetic energy directly related to velocity? But what you have to make sure that you incorporate is the m, which is probably what? The mass. Okay, that's the mass of it. And so that's where it gets thrown off. All right, and then the nature of liquids. And then we won't do boiling, but we're going to do just above boiling point. So the particles in liquids are in motion. And so they're sliding past one another and flowing. However, the particles are attracted to each other, and the forces between the liquids, we called them IMFs, but they're also called, starts with an A, intermolecular forces, but that's IMFs. They're also called, starts with an A. What kind of forces are they? They're forces of attraction. Nice. They're called, I know you knew it, attractive forces. And IMFs simply are the forces where? Good. Say it. Between the molecules. And the stronger the forces, the stronger you have the forces, then what about how the molecules? They must be, yeah, closer. Good, the closer the molecules are. Evaporation and vapor pressure. If you leave some water in a cup on the counter, after a week you'll observe that much of the water has done what? Yeah, evaporated. Good. And the word evaporated is different from vaporized, so we're going to talk about the difference. What's happening is the molecules that are at the surface of the liquid, and it's not boiling, okay, will escape into the gas phase. When the attractive forces are overcome, the liquid will actually change into gas or vapor. where the distance between the molecules does what?
Increases.
Yeah, increases. So in the gas state, those molecules are further away from one another. Evaporation is a cooling process similar to a human perspiring. So the high kinetic energy molecules escape, leaving behind the cooler molecules. So let's ask this question. And this is something that you've probably may or may not have thought about before. But it's a really, really hot day. Maybe you think about you were on vacation, you were in Florida, and let's say that it was 90 to 95 degrees out, okay? And you are sweating and you're dying and you're like, oh my gosh, just played a game of volleyball and I'm really hot. I'm going to go and jump in the ocean or in a pool or whatever it is. So you come out, no breeze. It's super hot. There's not a single breeze. You were burning hot before you got in the water. And you come out, and now after a little bit, you start to shiver. And you're cold. And the question is, why? Why is it that you're cold? Yes?
Because when you sweat, like the water, like takes some of your energy from.
Okay, but this is you're in the water, and you're coming out. Yeah, so this is you're in the water, and now the temperature is still the same. You were sweating before you got in the water. Now you come out of the water, and now you're feeling cold. Yes?
Is it because the water is absorbing your heat and then evaporating?
Nice. Guess what the molecules do to you?
Take your energy.
They take your energy. They take your energy. Everybody wants to be free. Do you agree? Raise your hand if you want to be free. Yes, everybody wants to be free. Okay, we all want to be free. And we're made of molecules, so it's only natural that molecules want to be free as well. And the idea is that these molecules, once they're in the gas state, are free. Okay, but it takes energy for those molecules to be able to escape. So we start off and we have water that's on the surface. So imagine that you have water, you put your hand in really hot water, okay? And you take your hand out, and it doesn't even take 10 seconds, and what has happened? You're cold, okay? If you try to transfer that to someone else, and you're like, hang on a second, I'm going to get you some hot water, and you put your hands under the sink and you've got hot water, and you come over, by the time you walk over to that person to give them the water, what's happened? It's now cold. And it's on the ground. Yeah. Okay. So the thing is, though, if you put it in a cup and you transferred it, would that water still be hot? Yes, it'll still be really hot. And I went back and got hot water from the sink back there, and it was still hot when we got in here to pour for that boiling of water with ice lab. So what's the difference? What's the difference in a cup versus having it on your skin? You want to try? The energy source. So the idea is that they're going to try to take the energy from you, and since that energy is available, those molecules will take that energy from you. But before that happens, the molecules aren't taking energy from you yet. The molecules that are on the surface are taking energy from where? No, on your arm. So you get out of the pool, and so now where are they taking the energy from first? But before they take it from you and your skin, where are they taking it from? The sun, the environment, and what else that's beneath them?
The water.
The other water molecules that are beneath them. Okay? There are other water molecules that are beneath them. Remember, it's millions and millions of these water molecules. Okay? So the idea would be that those water molecules are going to take energy from the ones beneath them. When they take that energy, that leaves them with what type of kinetic energy?
Higher.
The ones that left are now higher, and the ones that are still on your skin are now lower. So those are now cooler, and they're slower moving. So now those molecules want to escape that are cooler and that are slower moving. So what do those do now?
Get other.
There it's going to take energy from you. Okay? So now they take energy from you, making them have a higher kinetic energy so that they can do what?
Evaporate.
Evaporate and escape. Okay? If there's still water molecules left on you, those are going to be even cooler. Okay, that are left, because those are the slow-moving, really cool molecules. So try it at home. Hopefully you take a shower between tonight and tomorrow morning. Leave one leg. Don't dry one leg off. Okay, leave one leg with the water molecules, because if you dry it off, what happens? You're no longer cold anymore. Okay, and so those of you that are swimmers or divers that are in the pool all the time, you know this to be true. If you get out, you dry yourself off real quick, and then you're not feeling so cold anymore. Okay, So just leave like one leg with just water on it and just see if you notice that that leg ends up being cooler. So why do you get so cool? Let's try to sum this up in like 1 or 2 sentences. So the idea is these fast-moving high kinetic energy molecules, fast-moving high kinetic energy, high KE, I'm going to write MOLC for molecules. Fast-moving high kinetic energy molecules escape leaving behind cooler, slow-moving molecules. Then what do those molecules do? Those molecules then do what to you?
Take your energy.
They take your energy. Those molecules, MOLC, I'm going to put in quotes, steal your energy, leaving you feeling cool. Okay. And vaporization is simply just the conversion of a liquid to a gas, or you can also call it vapor. Depending on whether it happens at room temperature or not, that's the only difference between gas and vapor. Evaporation in a closed container. Imagine that you have a pot of water and it's covered with a tight-fitting lid. As time passes, the liquid particles are going to vaporize, and they collide with the walls of the container, creating a pressure that's known as, it's just the pressure of the gas.
Vapor.
We call it the vapor pressure. Awesome. It's known as vapor pressure. So all that vapor pressure is the pressure of the gas above the liquid. This is a force that's due to the gas, there it is, above the liquid. The liquid molecules will continue escaping, but eventually some of the particles will condense back into what phase? The liquid phase. So if you have a cover on top of your pot, those molecules are going to start to boil, they'll vaporize, but then since that top is covered, they have nowhere to go. So when you lift up the cover, what do you notice? Yeah, and a bunch of condensation that's dripping right on top. And you're like, wait a minute, I didn't put that there. I didn't get the top wet. I know that that was dry, and then I put it on, and now you've got condensation. And so it'll keep cycling. And as long as you have a tight-fitting lid, you will not lose any of that gas, and that could continue forever. If you're at 1 atmosphere pressure, then water would boil at what temperature? What do we say? At 100 degrees Celsius. Can water boil at a different temperature?
Yes.
Yes. Okay. Depends on the pressure, and that's kind of what you're going to be doing a little bit of that research on too. When the rate of evaporation of the liquid is equal to the condensation, so the evaporation is equal to the condensation, what would you call that? Nice. You'll call that the equilibrium vapor pressure. We'll just write, we call that equilibrium. At this point, there's no net change. It doesn't stop, but there's no net change between the two states. What if the temperature were increased? Since more liquid particles can be converting into gas, then your vapor pressure would also increase. Okay, I want you to skip to, let's just sum up. Oops. Right above where it says, pretty bitch, vapor pressure sum up. You know what, I do want to introduce endo and exo real quick to you. We'll do endo and exo real quick. So the vapor pressure is the pressure that's exerted by the what? It's the vapor pressure, so it's just the pressure exerted by the?
Vapor.
Yeah, by the gas, good, or the vapor. In equilibrium with its liquid, the vapor pressure of a liquid depends only on 2 things. It depends on, you can change how much gas you have by doing what?
Temperature.
Increasing the temperature. So it depends on the temperature. And it also depends on, some things have more gas at any one temperature. What do you think it's based on? We've kind of talked about this.
Pressure.
It's based on its own
Weight. Molar.
what is, something's a gas, something's a liquid, something's a solid. It's all due to its 3 letters. IMFs. Nice. It's all based on the IMFs and simply just saying the nature of the liquid. The nature of the liquid and its IMFs. Okay. At any one temperature, different liquids do have different vapor pressures, so they're not all the same. As you increase your temperature, the vapor pressure always increases. Good. For every liquid, it always increases. Okay, and then let's just do endo-exo. So I'll come back. We're not going to do pretty bits just yet, but we're going to do endo-exo. Before we begin, we need to revisit the definitions of exo and endo in terms of systems and surroundings. Exo sounds like out and exiting, okay? So an exothermic change is one in which the heat flows from the system to the surroundings, so energy is being released or, I heard, lost? So think of this as energy exo-exiting. Okay, so exiting. Endo is one in which the heat flows from the surroundings to the system, so energy is being absorbed or, starts with a G, gain. Thank you. Think of this as energy entering or endo entering. Yeah, that sounds like a good one. Endo entering or into, something like that. Okay, we'll come back to this problem later. Flip. So let's just do some examples of endo and exo. So for exo, we're going to relate the X to the letter using a freezer. The X and the Z are going to go together. So we're going to say these a couple times in just a second. For endothermic, we're going to think about, instead of using a freezer, what will be the opposite?
Microwave.
Yeah, or a stove. Okay, so it's going to be endo, stove, exo, freezer. So everybody say exo, freezer, endo, stove. Exo, freezer, endo, stove. One more time. Exo, freezer, endo, stove. Now you can have reactions where energy is being released, and so the reaction just loses energy and it feels hot. But what we're talking about here is we're talking about phase changes. And when you have phase changes, it's different. Because what's true of the temperature when it's going through a phase change? When it's going through a phase change, what's true of the temperature, everybody? It stays constant. Okay, so your temperature is not changing. So we can't say our temperature increased or our temperature decreased. So what we're going to talk about is, we're going to say, was energy absorbed or was energy released? When it was, if it's an exothermic example. So where would a freezer help? If you were trying to do what?
Make popsicles.
So you have liquid and you're turning it into? A solid. Perfect. Liquid to solid, which we call freezing. Or solidifying. Okay? So liquid to solid, or what else could a freezer help with? If you had gas and you wanted to turn it into? A liquid. That is called? No.
Condensing.
Condensing. Very good. Condensing. Okay, and there's one more.
Yes.
No, oh, you're not. Gas to solid. Gas to solid is not called sublimation. Do you remember? It starts with a D. Nice. Deposition. That's called deposition. So we're kind of coming back to what we had talked about at the beginning of the year. Now let's do the opposite. So the idea is that any of these, in order for the molecules to get closer to one another, for them to get closer to one another, energy is actually released. It releases energy as they come closer together. So as your molecules get closer, it releases energy. Now let's do the opposite. Where would a stove help? Or, yeah, so let's do solid to liquid. So solid to liquid, meaning that you're melting. What else? Good, liquid to gas, but we're not going to call it evaporating. We're either going to call it vaporizing or
Boiling.
boiling. Awesome. Vaporizing or boiling. And the last one is sublimation, solid going to gas, where you have it subliming.
What's an example of that?
Okay. So if you have carbon dioxide, solid carbon dioxide, dry ice, if you've ever seen it, it just starts to go sublime and completely go into the gas state.
Burn myself.
All right, and then we'll do more of this after, and that's the end of our first part of the states of matter notes.
We can turn it on.